Hello everyone, today my topic of presentation basic of digital electronics, in which I tell you how a computer understands different number system. Here, a computer understands information composed of only zeros and ones. The decimal number system is convenient for programming. A computer uses binary digits for its operation. We having a different number system. Decimal number system, binary number system, hexadecimal, octal system. Now, the first is decimal number system. It starts from 0 and ends with 9. It's having a base of 10. It is a decimal number 4598. Here, each digit is represented by its weight. For example, 8 is multiplied by 10 to the power 0. Here, 8 having a position of 0 and its weight is 10 to the power 0. And 9 is at a position of 1 having a weight of 10 to the power 1. And 5 is a position of 2 having a weight of 10 to the power square. And 4 is, is at a position of 3 and having a weight of 10 to the power 3. When we all combine these things, then it will form 4598. Similarly, in binary number system, we have two digits, 0 and 1, which having a base of 2. It is a binary number. For example, binary number 1011, where 1 from right side we start our positioning, give positions. 1 having a position of 0, and again 1 having a position of 1, 0 is position of 2, and next then the last is 1, it is having a position of 3. When we combine all these, from right side, 1 is multiplied by its weights, 2 raised to power 0, and the next one is multiplied by 2 raised to power 1, and the next and 0 is multiplied by 2 raised to power 2, and last one is multiplied by 2 raised to power 3. When we form, after that, it will form a binary number, which is 1011. Now, next is hexadecimal number system. In hexadecimal system, it is similar up to decimal number 0 to 9, but after that, it starts from A and ends with F. It starts from 0 and end with F. It's having a base of 16. Here, it is a hexadecimal number 1A5D, where D having a position of 0 and 5 is a position of 1, and A having a position of 2 and 1 is a position of 3. When we are combine this, it is multiplied by its weight. Here, the position of E digit in hexadecimal number indicated the magnitude of quantity represented and can be assigned a weight. The weight for a whole number are positive power of 16 that increase from right to left and begin with 16 raised to power 0, which is equal to 1. Now next is octal number system, where octal number system, it starts from 0 and ends with 7, where it is having a base of 8. Now, similarly, 5273, it is a octal number, and in which octal it is this octal number, it start from right side, 3 is at a position of 0 and 5 is at a position of 3. When we combine all these, each digit is multiplied by its own weight according to their position, where the position of each digit in this octal number system indicates the magnitude of the quantity represented and can be assigned by its weight. The weight for the whole number are positive power of 8 that increase from right to left, and it's begin with 10 raised to power. It begin with 8 raised to power 0, which is equal to 1. This is a conversion in basic number system. When we convert one number to other number system, this table we can use. Here we saw that where in binary number system, 15 is represented by 111. In hexadecimal number, 15 is represented by F, 10 is represented by A, In octal number system, 7 is similar to a decimal number, but 8 is represented by 10, 9 is represented by 11, 10 is represented by 12, and 11 is represented by 13, and 12 is represented by 14, and 13 is represented by 15, and 14 is represented by 16, and 15 is represented by 17. And ABCD in hexadecimal number, where 10 is represented by A, 11 with B, 12 with C, and 13 with D, and 14 with E, and 15 with F. And in binary number system, these after 2, the number of digits in binaries increases. It starts from 2 to 3 and up to 4 digits. This is a binary to decimal conversion. We having a binary number which is represented by 10101, and each digit having its position. It is represented by 1, 2, 3, 4, 5. Each digit is multiplied by its weight according to their position, and after multiplication and addition, the number will form that is known as decimal number 21. So it is a binary conversion from that 5 digits into a 2-digit decimal number. Now next is 5A9. It is a hexadecimal to decimal conversion from base 16 to base 10 conversion, where we having a number of 5A9, which having a bit position 0, 1, 2, where each position according to where this each digit is multiplied by their weights according to their positions. 9 having a position of 0, and A having a position of 1, and 5 have a position 2. And is multiplied, 15 is multiplied by 16 square, A is multiplied by 16 to its power 1, 9 is multiplied by 16 to the power 0, multiply with base. So they, after multiplication and addition, the number is formed in decimal form 1449. Now next is 645, that is the octal number which having a base of 8. It having a base with positions 0, 1, 2, where 5 is multiplied by base 8 raised to power 0, and 4 is multiplied by 8 raised to power 1, and 6 is multiplied by 8 raised to power square. After addition and multiplication, we got the result 421. Now next, decimal to binary conversion, where firstly we having a 39 number. It is divided through concept divide through by 2. 39 is divided by 2. We get question 19 and remainder is 1. That question 19 is again divided by 2. We got question 9 and remainder is 1. Again 9 is divided by 2. We got question 4 and remainder is 1. 4 is again divided by 2. We got question is 2 and remainder is 0. Again 2 is divided by 2 and we got quotient is 1, remainder is 0, and next last is 1 is divided by we got quotient is 0 and remainder is 1. Until we got quotient is 0, the division method is continued. From here, from when we started a number is divided by 2, that is known as LSB, and the last number we got as a remainder, which is known as our MSB. Though 39, when 39 is divided by 2, divided throughout by 2, we got a binary number 100111. It starts from here 100111. Now next is divide through by 16. Here decimal to, here we convert a decimal number to hexadecimal number, in which a number is divided by 16, because we want to convert decimal to hexadecimal. Here we convert base 10 to base 16, where 35 is divided by 16. We got a result of quotient 2 and remainder is 3. Now quotient 2 is again divided by 16. We got a result, quotient is 0 and remainder is 2. That last remainder is known as our MSB, and the previous one is known as our LSB. The number is 23 we got from right to left. 23 is represented by hexadecimal. Next is decimal to octa conversion, where similarly we convert decimal number into octadecimal number. As a divided throughout by 8, as 461 is a decimal number which is divided by 8. We got quotient 57 and remainder is 5. And again 57 is divided by divided by 8, we got quotient 7, remainder is 1. 7 is again divided by 8, we got quotient is 0, remainder is 7. That is the last when we got our quotient is 0 and remainder is 7. That is known as our MSB. And the previous one from starting, which is known as our LSB. We move from right to left, that is represent our octadecimal number 715. Now, binary to hexadecimal number. In binary to hexadecimal conversion, firstly, we have got a large series of binary numbers, which having a base 2. Now, we have to convert into hexadecimal. For each hexadecimal number is represented by 4 bits. So, what we do? Firstly, we divide that series of binary number into a 4 bits, group of 4 bits. After doing this, each 4 bit is represented a hexadecimal number. We put equivalent this 4 bit number by a hexadecimal number, and that number will form is known as hexadecimal number 5D9, where 101 is represented by 9, 1101 is represented by D, 1001 is represented by 5. We can understand by doing this by seeing the table where we have different conversion starting. For example, here you saw that 9 is represented by this. This number 9 is represented by 1101. So we can do this by use of decimal number converter table. Now that's binary to octal conversion. In binary to octal conversion, each binary number is a binary number, each digit of binary number, here where 3 digit is represented by equivalent octal number. So we divided this series of binary into a 3-bit group, 3 bits group, and that 3-bit group is represented by a octal number. So 100 is represented by 4, and 111 is represented by 7, and 101 is represented by 5. 574, which is represented a octal number. Now next is hexadecimal to binary conversion. What we do? Firstly, we write down the hexadecimal number. Now each digit is represented by 4 binary numbers, 4 binary digits, 4 binary digits. So 5 is replaced by 010, a 4-digit binary number, and C is represented by 10000. So that is C, equivalent of C we replaced here. Now combine all these binary by the binary digit, and it will form a binary that is known as hexadecimal to binary. Now octal, where each digit is represented by 3-bit binary number. 4 is represented by 100, 3 is represented by 000111, and 6 is represented by 110. So when after that combine all these digits with form a binary number which having a base of 10. Now hexadecimal to octal conversion. Firstly, what we do? We having a number 4DF16, 4DF which having a base of 16. Now each number is represented by 4-bit binary. 4D is represented by 4-bit binary. 5F is represented by 4-bit binary. Now, after doing this, combine all these numbers. Now, next what to do? We are applying a 3-bit division method here, because we have an octal number. We have to convert into octal form, and in octal, 3-bit binary is equivalent to 1 octal number. So these 3-bit binary number is equal to 7. 011 is equivalent to 3, and 011 is represented by 3, and 010 is represented by 2. Now after that, combine all these, it will form a 2337, which is equivalent to 4DF. Now next is octal to hexadecimal conversion. In octal to hexadecimal conversion, where 4568 is a octal number which having a base 8. Now each digit is represented by 3-bit binary number. 5 is represented by 101, 6 is represented by 110. Now combine all this, it will form a binary number, and this binary number is again by doing a 4-bit division. Here, because each digit of hexadecimal number, 4 digit binary number, is equivalent to 1 octal number. So these 3 digit is represented by 3 bit binary number, 5F is represented by 1 octal number, and 110 is represented by 2. So combine all these, it form will form a binary number, and this binary number is again by doing a 4-bit division. Here, because each digit of hexadecimal number is equivalent to 4-bit binary number. So what we do with a 4-bit division, we start from right to left by doing this and this, and other numbers we are placing a zeros. For the last one we are placing a zeros here, so we make it a 4-bit binary. Now each 4-bit is equivalent to one number of hexadecimal. So 110 is equal to E, 0111, 010 is equal to 2, 001 is equal to 1. After that, combine all these, it will form a 12E, which is hexadecimal number.